Assalamu alaikum, brothers and sisters. Welcome to the journey of quest where we quench your thirst of knowledge. Have you ever wondered how a seemingly ordinary rock can transform into a precious gem? The secret lies in the intriguing world of mineral transformation. This remarkable process is a cornerstone in the study of geology, shaping the earth beneath our feet and creating the dazzling variety of minerals we see today. The transformation of minerals isn't just an uncanny display of nature's magic, it's a fundamental process that unravels the mysteries of the Earth's interior. From the formation of diamonds deep within the Earth's mantle, to the creation of quartz in your backyard, mineral transformation is an integral part of our world. But how does this process occur? How can one mineral morph into another entirely different specimen? To answer these questions, we need to explore three crucial concepts: polymorphism, polytypism, and polysomatism. To understand how minerals can undergo such drastic changes, we must delve into the fascinating concepts of polymorphism, polytypism, and polysomatism. Before we move any further, let's take a closer look at polymorphism and its impact on mineral transformation. Polymorphism is a fascinating phenomenon influenced by various factors, primarily temperature and pressure, but it's not just these physical conditions that play a role. The chemical environment, the presence of other elements, and even the rate at which a mineral cools can all impact polymorphism. Imagine a mineral as a troupe of dancers, moving and shifting in response to the music. The music here is the environmental conditions, temperature, pressure, and the surrounding chemical environment. As the music changes, the dancers adjust their steps, forming different patterns and arrangements. Similarly, under different conditions, the atoms within a mineral rearrange themselves, leading to different crystal structures, or polymorphs. This remarkable ability of minerals to change their structural dance based on environmental conditions is what gives rise to the vast array of minerals we see today. In fact, it's the reason why we have precious gems like rubies, emeralds, and diamonds. For instance, the formation of a diamond, one of the most coveted gems, is a result of carbon experiencing intense pressure and high temperatures deep within the Earth. This extreme environment forces the carbon atoms to rearrange into a diamond structure, creating a gem that is not only beautiful but also one of the hardest substances on Earth. Polymorphism truly is a marvel of nature, enabling the creation of diverse and beautiful minerals. It's a dance of atoms, a ballet of nature, choreographed by the forces of temperature, pressure, and chemistry. So the next time you hold a precious gem or even a common rock, remember the intricate dance of atoms that gave it its unique form. Polymorphism, from the Greek words poly meaning many and morph meaning form, is a process that allows minerals to have more than one crystal structure. Let's delve into this fascinating world of polymorphism. It's all about the ability of minerals to exist in more than one form, depending on factors such as pressure and temperature. Fundamentally, polymorphism is a phenomenon that allows for the diverse array of minerals we observe on Earth and beyond. Let's consider carbon, a common element we all know. Now, carbon can exist in two distinct forms: graphite and diamond. It's the same element, mind you, but due to changes in conditions, such as pressure and temperature, carbon atoms arrange themselves differently, leading to these two distinct structures. Graphite, as we know, is soft and used in our pencils, while diamond is one of the hardest substances known to us. This is a classic example of polymorphism. Now you may wonder, why does this matter? Why should we care about polymorphism? Well, you see, understanding polymorphism is crucial for several reasons. It helps geologists understand the formation and transformation of minerals. For instance, the transformation of graphite to diamond under high pressure and temperature conditions gives us insights into the deep workings of our planet. Moreover, polymorphism also plays a crucial role in industries such as pharmaceuticals and materials science. In pharmaceuticals, different polymorphs of a drug can have different levels of solubility, which can impact the drug's effectiveness. In materials science, different polymorphs of a material can have different physical properties, like hardness or electrical conductivity, that can be exploited for various applications. So, in a nutshell, Polymorphism is not just a fascinating natural phenomenon, it's also a concept of immense practical importance. It's a testament to the marvelous versatility of nature, showcasing how a single element can exhibit such a wide range of forms and properties. As you can see, polymorphism is a fundamental concept that allows us to understand the diversity of minerals. Now that we've introduced polytypism, let's delve deeper into this fascinating phenomenon. You might be wondering, what really influences polytypism? Well, much like polymorphism, environmental factors like temperature, pressure, and the rate of crystal growth play a significant role. However, the magic of polytypism really unfolds when we start exploring the different structural forms a mineral can take due to this phenomenon. Remember silicon carbide from our previous discussion? It can exist in over 200 different polytypes, each with its own unique properties, but all retaining the same chemical formula. This is the magic of polytypism. Even the subtlest of changes in the atomic arrangement can lead to a new polytype, making the mineral world incredibly diverse and fascinating. Now, let's look at the role of polytypism in the mineral transformation process. While polymorphism explains the transformation between different forms of a mineral like carbon into graphite or diamond, polytypism adds another layer of complexity. It explains why a mineral can exhibit different properties even while retaining the same chemical composition, just by tweaking the arrangement of its atoms. This is crucial in fields like materials science, where a slight change in atomic structure can result in a material with entirely different properties. To sum it up, polytypism adds another layer of complexity to the world of minerals, proving that even the smallest changes can have a big impact. It's like having a wardrobe full of outfits made from the same fabric, but each outfit is unique in its own right. Stay tuned as we delve deeper into the intricacies of mineral transformation. Next up, we have polytypism, a fascinating phenomenon where a mineral can exist in multiple structural forms. Picture a mineral walking into a wardrobe and emerging as a different version of itself, not by changing its chemical composition, but by rearranging its atomic structure. That, in a nutshell, is polytypism. It's a bit like a chameleon, adapting its form without losing its essence. Now, you might be thinking, isn't this just like polymorphism? Well, not quite. While both involve variations in structure, the key difference lies in the dimension of variability. Polymorphism involves changes in 3 dimensions, while polytypism, on the other hand, is more subtle. It's about variations in 1 dimension, usually along the crystallographic axis. Think of polytypism as a more refined, selective version of polymorphism. So how does this transformation occur? The answer lies in the conditions during the crystal's growth. Variations in pressure, temperature, or other environmental factors can lead to different atomic arrangements, resulting in different polytypes. And these changes can be as subtle as a slight shift in the stacking sequence of the mineral's layers. Let's take silicon carbide, for instance. This compound, often used in cutting tools due to its hardness, showcases polytypism beautifully. Silicon carbide can exist in over 200 different polytypes, each with its own unique properties, but all retaining the same chemical formula. It's like having over 200 different outfits made from the same fabric. So, what's the significance of this chameleonic trait in minerals? Well, polytypism is integral to the mineral transformation process. It helps explain why a single mineral can have such a wide range of properties, opening up a whole new world of possibilities for their usage in various industries. Polytypism, while somewhat similar to polymorphism, provides another layer of complexity to the mineral transformation process. It's a testament to the incredible adaptability and diversity of minerals, proving that even the smallest change can make a world of difference. Let's make a short pit stop on our journey through the transformation of minerals to unpack the concept of polysomatism a bit more. As we've discussed, polysomatism is all about the replacement of elements in a mineral's structure. But what triggers this fascinating process? The answer lies in the conditions that the mineral is subjected to. High pressure, high temperature, or a combination of both can initiate the process of polysomatism. Picture it as a pressure cooker situation, where the mineral undergoes chemical reactions that trigger the replacement of elements. Now imagine a mineral structure as a puzzle. In polysomatism, some of the puzzle pieces which represent elements are swapped out for others. However, even with these changes, the overall picture of the puzzle, the mineral's structure, remains the same. This is the crux of polysomatism. So why is this process so important? Let's put it into perspective. Polysomatism is like the chameleon of the mineral world, constantly adapting its composition to survive in different conditions. This ability to alter a mineral's composition is crucial in the transformation of minerals, influencing not just the mineral itself, but the overall geology of the Earth. Moreover, the understanding of polysomatism is key for geologists and petrologists, as it helps them predict and understand geological phenomena, assess mineral deposits, and even aid in the exploration of other planets. Polysomatism, in all its complexity, is a testament to the dynamic nature of minerals. Even under extreme conditions, they find a way to adapt and transform, proving that change is indeed the only constant. Finally, we have polysomatism, a process that involves the replacement of certain elements in a mineral's structure. Let's roll up our sleeves and delve deeper into this fascinating process. Polysomatism, to break it down, is a mineralogical concept where one or more elements in a mineral's structure are replaced by other elements without changing the mineral's overall structure. Picture it as a game of musical chairs, where the players are elements and the chairs are the spaces in the mineral's structure. When the music stops, some elements find themselves replaced by others, yet the game, or in our case the mineral structure, remains the same. But how does this happen? This process typically occurs under conditions of high pressure and temperature, where minerals are subjected to chemical reactions. These reactions trigger the replacement of elements, with new ones stepping in to take their place. Let's illustrate this with an example. Consider the transformation of olivine to serpentine. Olivine, a green mineral often found in igneous rocks, can transform into serpentine under certain conditions. When olivine is exposed to water at high temperatures and pressures, the magnesium in its structure can be replaced by other elements like silicon or oxygen, leading to the formation of serpentine. Despite the change in composition, the overall structure remains the same, which is the crux of polysomatism. So, why is this significant? Polysomatism plays a crucial role in the transformation of minerals, influencing the mineral composition of rocks, and hence the overall geology of the Earth. It can also lead to the formation of new minerals, contributing to the diversity and complexity of the Earth's mineral kingdom. Moreover, understanding polysomatism is key for geologists and petrologists. It helps them predict and understand geological phenomena, assess mineral deposits, and even aid in the exploration of other planets. Polysomatism, with its ability to alter a mineral's composition, plays a vital role in the transformation of minerals. Understanding mineral transformation isn't just for geologists, it's also crucial for many industries. Let's explore some practical applications. Polymorphism, polytypism and polysomatism are fundamental to processes in various sectors. For instance, the gemstone industry relies heavily on these transformations. The formation of precious stones like diamonds, emeralds and rubies is deeply tied to polymorphism and polytypism. The unique physical properties of these gems, such as their hardness and luster, are a direct result of their atomic arrangements. Polysomatism plays a significant role in the formation of other valuable materials. For example, the transformation of limestone to marble, a highly prized material in the construction and sculpture industry, is a result of polysomatism. But the applications of these processes aren't limited to just gemstones and construction materials. They also have potential in technology and industry. For instance, the semiconductor industry leverages the properties of silicon, a product of mineral transformation, for the manufacturing of microchips. In the future, understanding these processes could lead to the creation of new materials with tailored properties for specific applications. From jewelry to technology, the transformation of minerals plays a crucial role in our everyday lives. As we continue to explore and understand these transformations, who knows what exciting discoveries lie ahead. We've journeyed through the complex world of mineral transformation, understanding the roles of polymorphism, polytypism, and polysomatism. Let's take a moment to recap these fascinating processes that shape the world beneath our feet. We started with polymorphism, the ability of a mineral to exist in more than one form, or polymorph due to variations in temperature and pressure. Each polymorph has its own distinct set of physical properties, yet they all share the same chemical composition. Think about diamond and graphite, two forms of carbon with drastically different properties due to their unique structural arrangements. Next, we delved into polytypism, a form of polymorphism where variations occur in the stacking sequence of atomic layers. The classic example is the mineral group of serpentine, displaying multiple polytypes that result from different stacking arrangements of the same layer. Polytypism plays a crucial role in determining a mineral's physical properties, including hardness and luster. Then we explored polysomatism, the process where existing minerals are replaced by new ones without the rock's overall shape being altered. This fascinating process is driven by fluid rock interactions leading to the formation of new minerals that are stable under the prevailing conditions. An example of this is the transformation of limestone to marble through the process of metamorphism. Each of these concepts, polymorphism, polytypism, and polysomatism, plays a vital role in our understanding of mineral transformation. They help us comprehend how the same basic elements can rearrange themselves into a myriad of different minerals, each with their own unique properties and appearances. These transformations are not just academic curiosities, they have practical implications too. They influence everything from the formation of precious gemstones to the distribution of valuable minerals within the Earth's crust. Next time you look at a gem or a piece of rock, remember the intricate processes of polymorphism, polytypism, and polysomatism that contributed to its formation. The world of minerals is indeed a world of transformation. As we've explored the complex world of mineral transformation, we've learned about the incredible processes of polymorphism, polytypism, and polysomatism. These are not just textbook terms, they are intricate, dynamic processes that shape the very world beneath our feet. They transform simple elements into a wide variety of minerals, each with its own unique properties and appearances. They're the reason why a diamond sparkles in the light, why a serpentine stone has its characteristic luster, and why a piece of marble has its distinctive texture. Understanding these processes is not just important for geologists. It's also crucial for anyone interested in the natural world, from gem enthusiasts to hikers, and even artists trying to capture the beauty of the natural world in their work. So let's keep exploring, keep asking questions, and keep being amazed by the wonders of mineral transformation. After all, the world of minerals is indeed a world of constant transformation, and there's always more to discover. Thanks for watching us. Share our videos, subscribe our YouTube channel, and press the bell icon and stay curious for new uploads.